We've seen that a current-carrying wire experiences a force when placed on a magnetic field. We also know that current is simply electric charges moving through a wire. It makes sense then that freely moving electric charges would also experience a force when they pass through a magnetic field. Well, this is not simple to set up in a lab. Experiments have shown that this is exactly the case. To find the magnetic force acting on a single electric charge, we can look at our expression for the force of a current moving through a wire. From here, we can get a bit creative with our equations. We know that if some number of particles with a charge of Q pass by a point at some time t, this defines the current. We would like to get rid of that length if we can, since we are looking at a single particle. So we can think back to the very beginning of Physics 1 and remember that length can be expressed as the velocity of a particle times the time. This we can substitute into our magnetic force equation. The times will cancel out, and if we are talking about only one electric charge, N is equal to 1. And we find the magnetic force acting on a single electric charge to be the product of the magnitude of the charge, its velocity, and the strength of the magnetic field. And as before, if the charge is moving at some angle to the magnetic field, we would need to take the sine of whatever angle that is. So again, notice that if the charge is moving parallel to the magnetic field lines, the magnetic force acting on the charge is 0, and the force is greatest when the charge is moving perpendicular to the magnetic field lines. Now the direction of the force can be found using yet another right-hand rule. Orient your hand so that your outstretched fingers are aligned in the direction of the magnetic fields. Your thumb should point in the direction of the velocity of the electric charge. The direction of the force will be the direction of your palm if the electric charge is positive. If the electric charge is negative, the direction of the force will act in the direction of the back of your hand. Suppose you place a 20 nanocoulomb positive charge onto a glass rod. Calculate the force on the rod due to the Earth's magnetic field if you throw it with a velocity of 10 meters per second due west. Really, we are looking at how much force the Earth exerts on a charge, and we are given all the information we need to find that force. Since the magnetic field is acting perpendicular to the velocity, we don't need to worry about any angles because the sine of 90 degrees is 1. So plugging those in, we find a force along the lines of 10 to the negative 11th newtons. Interestingly, the path of a moving charge through a magnetic field will not be in a straight line. The path of a charged particle actually moves in a circle. Now first off, we want to assume here that the magnetic field is uniform, and since these dots have X's in them, it indicates that the field is pointing into the page. So if we take a negative charge and start it moving in some velocity to the right, according to our right-hand rule, the force acting on the charge will be in the downwards direction. Since the force is perpendicular to the direction of motion, it does not work on the charge. If no work is done, the charge's kinetic energy and velocity do not change. The direction of the charge's motion, however, does change in the direction of the force. So now we are moving at the same speed, but in some other direction. We can apply our right-hand rule again and show that the force is acting perpendicular in the downward direction, and again changes the direction of the velocity. This will just keep going on and on. So the magnetic field actually supplies the centripetal force that keeps the charge moving. Many moons ago, we learned about centripetal force and that you can calculate it by taking the mass times the velocity squared divided by the radius. And today we learned the same force is equal to the charge times the velocity times the magnetic field. We can solve this for a lot of things, but usually what we're interested in is the curvature of the path of the circle. So for a charge moving through a uniform magnetic field, the force exerted by the magnetic field is in fact the centripetal force acting towards the center of the charge's motion. Remember that charges are going to move in opposite directions. In this example, we had a negative charge in a magnetic field going into the page that is forming a clockwise motion. If the charge would have been positive, the motion would have been in a counterclockwise direction. So calculate the radius of curvature of the path of an electron having a velocity of 6.00 times 10 to the 7th meters per second, perpendicular to a magnetic field. We are given the magnetic field and the velocity. We have known the charge of an electron for a while, and we can look it up if we need to. The same thing happens with the mass. So adding those into our equation, we get 0.683 millimeters. So a magnetic force exerts a force on a charge q moving with some velocity v through a magnetic field B. The direction of the force is perpendicular to both the magnetic field and the velocity of the charge, and can be visualized using a right-hand rule. The charge will move in a circular path with a radius equal to the mass times the velocity divided by the charge and magnitude of the magnetic field.